So having learned about the two different systems, but equivalent system for representing a two-dimensional points, and also how you set up a valid test case. So that's something we spoke about earlier. If you got any doubts, please review before you proceed. Let's now see how we can implement both the classes and also test case on in Java. Okay, so there are two keywords you have to learn. Okay, one is about interface over here, right? So you can see public interface, public meaning that it's going to be visible throughout all the classes across packages. And also we got an interface called points. And notice that this is something very similar to the abstract methods, except that we don't have the abstract keyword over here declared. You can think about informally, it is because if every method in the interface is actually abstract, then we don't need to really emphasize that they are simply just abstract. So by definition, all the methods inside a particular interface, you should not have any implementation for that. You can see you only declare maybe the name of the method, and sometimes you may have some parameter list, and you just got semicolon, pretty much like an abstract method, but you don't really use the abstract keyword. Let me visualize this a little bit. So this is our interface points over here, right? The new keyword you have to learn is interface over here. And for every class, that's more like for every subclass for the interface, you have to say increments. So you can see Cartesian points increments the points, and also polar points increments the points. So these are the two new keywords you have to learn. All right. First of all, you can see we got interface over here, the first keyword, and also second keyword is about increments. And don't forget, in the case of abstract classes, you still say extends, right? You would say, for example, rectangle extends polygon, which is an abstract class, and also triangle extends polygon. But in the case of interface, you gotta say increments, right? Okay, over here. Okay, what's more? You can see here, usually all the methods for the interfaces, they should be made available to all the classes, right? They should be available, okay? Available across packages. Okay, that's really important. You don't really say protected or private methods. You don't normally you don't really declare any private methods or protected methods in the interface. They should all be public, okay? And then what's more, let's see this part over here. You can think about this part here, double, and also get x, get y. Okay, let me just do better. So these are the headers of the methods. Okay, so these are the headers. Headers of the methods, including the return type in the case of accessor, and also get x, get y, the names of the methods. And in this case, the list of parameters is simply just empty. But in general, it may be non-empty, depends. Okay, and it's also very important to notice over here. You can see we simply got semicolon over here, right? So that means the implementations deferred to subclasses, which will be either Cartesian points, where we try to implement get x and get y in a different way, from, in the case of polar points, we actually got get x and get y implemented in a different way, right? But they will be implemented, okay? And as I said before, informally, you can think about the interface is more like an abstract class where all the methods are simply abstract, informally, okay? Okay, let me just say one more thing, just put one more notes. Okay, it's more like an abstract class where all methods are abstracts. But it's very informal thinking. That's not something you should really put formally in any answer, right? Just more intuitive way for you to think about. Since all the methods are simply abstract, there's no need for you to put any abstract keyword over here. So don't do that, right? If you say public abstract double get x, it's going to be some compilation error. Okay, hopefully that makes sense to you. Right? Let me take a look at the classes together. Right? There should be no surprise to you. you can see in the case of the Cartesian points, we are only storing the attributes x and y over here, right? So that's the absolute position. X and y. On the other hand, in the case of polar points, as we said before, it's going to be the relative position with the distance r and also angle phi. By the way, the phi should be measured in radians. Okay, that's something I will show you how to do the conversion by calling some helper method from the math class. So that's the relative position. And notice that all these attributes are simply just private, just following our normal practice. You can see private over here, and also here we got private here, and also private over here. Okay. Okay, let's now move on. And what about constructor? You can see for the constructor, we got Cartesian point versus polar points. In the case of Cartesian point, we just get x and y, right, over here. And for the polar points, we actually got r and phi, right, just to, of course, for the color of this constructor here, you have to make sure this is measured in radian. Okay, you will see exactly what I meant when we show the test code. Okay, so this phi over here should be measured in radian. Measure in radians. All right, and then what about get x and get y? It's now very important to see how they're implemented. You can see, for example, get x and also get y. So these are the methods that are actually required by the interfaces. You can think about all the methods that's actually from all the methods that are declared in the interface. They will force each subclass that implements the interface to implement them. Okay, so let's now try to make some notes over here. You can think about these two methods, and also they will also force, these two methods will also force them to be implemented over here. Okay, so you can see here we got get x and also get y. Okay, forced to implements. Okay, forced to implements. And let's see how they are implemented differently. In the case of Cartesian points, we simply return the x and return the y. That's really easy, right? In the case of get x and get y, we simply do the trigonometry computation. We say r times cosine 5 in the case of get x, and also r times sine 5 in the case of get y. Right? Just recall this diagram over here, right? This diagram that we spoke about earlier. Okay, I'll leave that to you for recall. All right, let's now take a look at the test case, right? As I said earlier in the module, so this particular test case, we simply got 2a, a times square root of 3, and also a. As long as you can replace a by some numerical value, the valid triangle will just be produced according to the scale. And let's now take a look at what we did. So here I simply got a, x, and y. So that you can think about the a over here is the a, little a over here. Okay, and I simply say a is simply just 5. And what about x and y, right? So x, you can see according to the scale, x will just be a times square root of 3. A times the square root of 3. And just remind you again, in the math class, as which I assume you learned in the first year, if you got any doubts, please let me know. I can point to you some reference. So here, math dot square root. So this is actually a static method from the math library class. Okay. All right. So this, since it's static, so you can simply invoke the method on just the math class name. You don't have to create some context objects of type math. You don't have to. And also y will just be a, right? You can see y is simply just a over here. So that's why you see y is simply a, right? So once we have set up all the values, let's now take a look at something very similar to how we discussed the abstract class. Okay. You can see point P over here. Let me use the lighter green, if I may. Over here, right? You can see the point over here is the interface class, right? So point over here, we know that it's the interface. Interface used as a static type, which is completely allowed. Like before, we actually used the abstract class polygon as a static type for polygon P. right? Similar. So now we know that P is actually statically declared as points, the interface. So now dynamically, what can it be? Well, it can be either of its subclasses or either of its implementing subclasses, right? It can be either Cartesian points or polar points, right? A very quick question right away, right? Before I go on. Can I write something like this? If I actually got points P, right? P is declared statically as the interface point. Can I simply say this? New and then points. Okay? Can I do that? Well, we actually got similar encounter before, right? Where we talk about if you got P declared as polygon, can you say new polygon? We said you could not, because otherwise at the runtime, if you say p.getArea was not actually defined in the polygon abstract class. Similar. So this will not be valid, right? Not valid. Meaning that it's not going to compile. But why? I'm going to describe verbally very quickly. You can prove by contradiction. If this was allowed, in that case, P will be pointing to some point objects at the runtime. In that case, if you actually try, for example, P dot get X, or if you try P dot get Y, both are legitimate expectation on the points class, right? The point interface, because you got get X and get Y. However, none of them is actually implemented. By definition, every method in the interface is unimplemented. So that means if you get p.get X, p.get Y, you will simply crash if the dynamic type was actually point, because there's no definition for get X and get Y. All right, so that's why it is not valid, right? So this will not be good. This will not be good either at the runtime. It will simply just crash. Okay, it's a very quick illustration that's very similar to what we did before. You will see something similar that's remarked in the slides. All right, let's now go on to the example code, and then I'll show you something, some illustration on the Eclipse as well in a moment. Okay, let's say the first line over here. So P is assigned to new Cartesian points x, y. Right, that's what we're doing. So what we're doing is we're calling the constructor for Cartesian points, which is defined over here, and we got x and y, right? X and y are simply these values, right? So it's going to be, in that case, it's going to be 5 times square root of 3 and also 5, right? That's going to be the value, right? And then when we try to print, right, we say p.get x and also p.get y. How many versions, by the way, do we have for the get x and get y? This get x and this get y, they wouldn't be counted as one version, would they? Because they simply have no body of implementation. So we only got 2 versions in the hierarchy. Version number 1 is here in the Cartesian points. Version number 2 is here in the polar points, right? So now we which version is going to be invoked depends on the dynamic type for the context objects, right? That's dynamic binding. So that's why what we have to do is we know that for the P, the context objects, right? The context objects, its dynamic type is, well, since it's actually pointing to some new Cartesian point, right? So point P is actually pointing to this object over here. So dynamically, it is Cartesian points over here. So that means it is going to call the version of get x and get y in the Cartesian points over here. These. Okay, Cartesian points. Okay, so that means get x and get y will simply call these versions over here. All right, similarly, let's say we try to do the next 2 lines. Let's say we say P is reassigned to new polar and these values over here, right? Let's now take a look. So what we're doing is we're calling this constructor over here, polar points, right? So that means we are actually calling this constructor over here, right? So 2 times A, 2 times 5, right? So that'll be R will just be 10. And also math.toRadian. So this is how we convert the degrees into radian, right? As I said before, the 5, when we do the calculation, it should be in radian, just mathematically. Okay, so now we say 30 degrees. Let's get its corresponding radian value. In that case, you can simply invoke in the math class. There's a static method called toRadians. You can just use it for free, right? We don't need to implement it from scratch. It'll be too complicated. So now in this way, it's going to be I'll just say 30 degrees. Okay, of course, the equivalent radian to the 30 degree. That's exactly what's being done over here. Okay, and let's say we say p dot get x over here, and also p dot get y. Right, we're calling these two methods. And which version that's going to be invoked depends on the dynamic type for p. Right. So after this particular reassignments, we know that p, rather than pointing to over here, it is actually going to point to over here. So that means dynamic type of p has been changed through reassignments into polar points over here, right? Over here. So that means we are actually going to invoke these two methods over here, version number 2, for get x and get y, right? Let me just make one more notes. So we know that at this point here, dynamic type for p is actually polar points. Okay, so nothing very complicated. You can see it's very similar to the principle we spoke about in the abstract classes, or even more in general about inheritance. Okay, let me see if there's anything else I want to mention. I think that's about it. Okay,